Hello and welcome back. If you've just completed that video I had on Kant and made it all the way through, good for you, congratulations. And if you are continuing on watching this video even after trying to slog through that last video on Kant, well, all the better. I'm now confident that you probably actually make it through to the final end of these lecture series. So what are we at now? Okay, here's where we stand at the end of Kant, at the end of like the 1780s. Kant asserted that our minds organize space our experiences into three-dimensional space and organize our experiences into a one-dimensional time. Our knowledge of geometry comes from our mind's organization of three-dimensional space, and we know nothing better than we know our own minds, and so therefore that's what the knowledge of the axioms of geometry rests upon. But that also means that to doubt, for example, the axioms of geometry is basically to doubt our own mind, and rational thought itself would be impossible without that. So whereas Kant was looking to set up rules by which we should reason carefully, just like scientists analyze carefully the limits of their instruments, similarly, we cannot doubt the truth of the axioms of geometry. That is just how our minds work, and that is a limit of our own mathematical or philosophical instruments. To doubt them would basically be to doubt our own rationality and to do the impossible. Okay, but still, people had troubles with the fifth axiom of Euclidean geometry, the parallel postulate. It's not that they doubted it, but they still thought it was so complicated that it should be provable from the previous four. Remember, the previous four axioms were considered axioms because they were the obviously true starting point of our definitions. Let's take a look again real quickly at this, at the axioms, some of the axioms, and what that fifth postulate said. So, for example, Euclid's first axiom, and this is in my own more intuitive words, are given any 2 points, you can connect them with a line segment. So, given 2 points, kaboom, kaboom, you can connect them with a line segment. That was considered pretty obvious, pretty true. Now, looking at the parallel postulate as Euclid had it, I'm not even going to write out the words because that'll take a long time. I'm just going to try to write a picture here to explain to you what it means. What Euclid's parallel postulate said is if you had two lines crossed by a common transversal like this. So these are two lines, boom, boom, and they're crossed by a common transversal. And their interior angles on one side added up to less than 180 degrees, less than 180. Then on the side where those angles add up to less than 180, if you continue to extend those lines, they would eventually meet. This really sounded like a theorem, not like a axiom, not like between any 2 points you can join it with a line. And so people thought that you should be able to prove that from the other four axioms. And over 2,100 years, people tried to prove the fifth axiom from the previous four. None of them succeeded, but many of them thought they had succeeded. So how did that happen? Well, obviously, many thought they succeeded because they made a mistake in their proofs. They made some mistake somewhere. And that's probably most of the supposed proofs of the parallel postulate from the previous four. But things can get a little more interesting than that. There are some mistakes, you could say, that people might make that are more interesting than they just made a mistake in their reasoning. A much more interesting problem that they came across was that they implicitly or explicitly assumed something that was equivalent to the parallel postulate. So for example, you might be more familiar with Euclid's axiom, Euclid's fifth axiom, in a form that's called Playfair's postulate. Playfair's postulate is that if you have a line and a point not on the line, there is exactly one line going through that point parallel to your given line. That is, there's exactly one line through that point that does not meet your given line. From this, you can prove Euclid's actual fifth axiom as that's stated. From Euclid's actual fifth axiom, you could prove the Playfair's postulate. So in a way, Playfair's postulate is equivalent to Euclid's axiom. They're essentially saying the same thing, but in different clothing. And lots of mathematicians over the millennia assumed things that said something different than Euclid's fifth axiom, the parallel postulate, but actually were equivalent to it, that from each one you can prove the other. And in a way, it's considered that they were implicitly, or again explicitly, assuming the axiom and therefore not really proving it from the previous four. Let's take a look at some other equivalents of Euclid's axiom. My students' favorite equivalence of Euclid's parallel postulate, the equivalent thing of Euclid's parallel postulate, is the following statement: rectangles exist. That's it. If you assume rectangles exist, you can prove the parallel postulate. From the parallel postulate, you can prove rectangles exist. What do we mean by rectangles? A rectangle is a quadrilateral with 4 right angles. If something like that exists, the parallel postulate is true. My students usually find this so obviously true that I kind of lose them in my argument that this is actually an ongoing issue in mathematics. They say that basically, if mathematicians didn't accept that this, adequately proves the parallel postulate, then they're just being intentionally obtuse. And this isn't really an issue. They're just making it an issue. Well, the thing is that by this time, the game is really proving the fifth axiom from the previous 4. They weren't really interested in including new axioms, even if those new axioms seemed as obvious and as apparent as the first 4. My students seem to think that rectangles exist is as obvious as, given any 2 points, you can connect them with a line, and therefore should be admitted. But really, by the time this came up, the nature of the game was no new axioms, even if they're obvious. You gotta prove the fifth one from the previous 4. Some other equivalences of the parallel postulate are that the sum of the angles in a triangle are 180 degrees. If you assume that the sum of the angles of the triangle are 180 degrees, you can prove the parallel postulate, sort of an axiom. What else is there? Oh yes, that you can have 2 triangles, each with the same angle measures, but of different sizes. So if you have triangles that this angle measures the same as this angle measure here is the same as this one, and this angle measure here is the same as this one, but that they are different sizes, from that assumption, you can prove the parallel postulate. But again, it's a new assumption you need to include in. So it's no longer the fact that, the original problem of the parallel postulate was it just did not seem obvious. It did not seem that it should be included in the list of obvious statements. But eventually, even if someone found a new statement that seemed as obvious as the previous ones to include, from which you can prove the parallel postulate, that was no longer considered good enough. The name of the game was proving the fifth parallel postulate from the other 4. You can't include anything new, even if it seemed as obvious as the first 4. So the nature of the game kind of changed. All right, now, in the 1700s, before Kant, a couple mathematicians, Saccari and Lambert, tried a new tack to prove the parallel postulate. What they did was they tried to prove it by contradiction. They assumed the negation of the parallel postulate and see that if they could get a contradiction. The idea of proof behind contradiction is you assume that what you're trying to prove is false, and if from it you reason correctly and get to some contradiction and impossibility, then your assumption that it was false itself must have been false. So therefore, what you're trying to prove must be true. So what they did was they assumed the first 4 axioms, and they assumed the negation of the 5th axiom, that it was false, and therefore concluded that if they can get to a contradiction, then that will have proven the 5th axiom from the first 4 by contradiction. That was their tack. So let's take a look at what the contradiction of the Euclid's parallel postulate might look like. Let me get a new sheet up here. So what that would say is if we have 2 lines with a common transversal, and on one side the sum of the angles is less than 180 degrees, that no matter how far we extend those lines, they are never going to meet. All right? This is what the negation of the parallel postulate would look like. Now, at this point, let me put in a comment. Some of you that know some non-Euclidean geometry might be a little confused at this point. It's commonly discussed that there are 3 kinds of geometry. There's Euclidean geometry and 2 kinds of non-Euclidean geometry, spherical geometry and hyperbolic geometry. However, spherical geometry actually contradicts some of the first four axioms, in particular the first one. So if you really are holding those first four axioms true and assuming the negation of the fifth one, you really are just dealing with hyperbolic geometry. Keep that in mind. If you don't understand what I said so far, don't worry about it. I'm just clearing up some confusion with some people that might have a little too much knowledge for these videos. All right. Now the thing is, from this assumption, they each derived this huge body of work, which was very weird. They had a lot of weird results. Like, for example, one result is, let's say you have two lines and they have a common transversal that hits each of them at right angles. Well, if the negation of the parallel postulate was true, that means these lines actually have to be moving away from each other as they move away from that common transversal. Furthermore, no other transversal to them can also have two right angles because that makes a rectangle. And remember I said that in non-Euclidean geometry, rectangles don't exist. So given any two lines, there's at most, if that, one common transversal that hits them both at right angles. What else? There's a lot of things. The angle sum of a triangle is less than 180 degrees. In fact, the angle sum of the triangle depends on the area of the triangle. If you know the area of the triangle, you can conclude what its angle sum must be and vice versa. So, a lot of weird stuff. Now, Sakurai, what did he do? He eventually made a mistake and forced a contradiction that isn't there. And he went to his grave thinking that his contribution to the history of mathematics is that he proved the parallel postulate by contradiction. Lambert never did that, never forced a contradiction that wasn't there, but he kept coming up with these weird results and said, well, this is really more and more evidence that the parallel postulate is true. So let me ask you this. Can either of them be said as to have had invented non-Euclidean geometry? Each of them, and I don't know if they were familiar with each other's work. In the book I'm getting this from, they don't mention it, so I'm assuming they weren't familiar with each other's work. But each of them were the first to develop a whole body of non-Euclidean geometry, like a whole set of results. This is non-Euclidean geometry. But Sakurai thought that his work actually disproved the possibility of non-Euclidean geometry, and Lambert, at the very least, thought that his work made it very unlikely. So how seriously do we have to include the authorial intent, the intent of the authors, what they thought about what they were doing, in attributing to them the construction, the creation of non-Euclidean geometry? Because, you know, on one hand, they were the first to create huge bodies of non-Euclidean geometry. On the other hand, that's not what they thought they were doing. So there we go. Now we're going to go ahead to the first people who actually thought this is what they were doing. Let's see. There was a mathematician. Now, this is in the early 1800s, so this is after Kant. This is when Kant stuff was big. A mathematician by the name of Farkas Bolyai wrote a letter to his son advising his mathematician son not to waste his professional life trying to prove the parallel postulate. He, the father, had wasted his life on this endeavor and really argued to his son not to try it. Well, the younger Bolyai did try it for a little while, but then had this inspiration. What if, assuming the negation of the fifth axiom, the parallel postulate, is actually okay? And it just develops a different kind of geometry than what we're familiar with. He, had that idea. And he started developing and proving out a body of non-Euclidean geometry in full awareness of what it was he was doing. His father saw that, thought, oh my God, it's brilliant. And contacted an old school friend of his, a guy by the name of Carl Friedrich Gauss. Now, Gauss is one of the towering names in mathematics. He was definitely the preeminent mathematician of his time and possibly, arguably, the greatest mathematician of all time. He had a huge reputation, well-deserved. Farkas wrote to Gauss and told him all about what Janos was doing and included as elements of subject matter. The father and son were probably disappointed with Gauss's response. Gauss's response was, oh, this is great. I could praise young Janos's work, But if I did that, I would be praising myself, because I myself have had these thoughts and developed these things, but I just didn't want to. Um, I didn't want to say these out loud because I would fear the howls of the Bohemians. By which he meant he knew that Kant's ideas were so ingrained in the society at the time that despite his towering reputation, that if he had given voice to these ideas about non-Euclidean geometry, his reputation would have been ruined. That is how ingrained it was. Now, a little after that time, there was a mathematician in Russia by the name of Nikolai Ivanovich Lobachevsky. And he had the same idea. Maybe this is just another alternate legitimate geometry. He assumed the negation of the fifth axiom, and he developed a whole body of it. The difference is he finally went public with this. He was the one that went to bat. He called down the howls of the Bohemians on his head, and he fought them. And there was a big debate and big struggle over this. Gauss, seeing him take up this sort of mantle, actually was in favor of Lobachevsky's endeavor. And eventually, mathematicians came to accept this idea that non-Euclidean geometry is just an alternate, valid geometry, and that therefore you can't necessarily really prove the fifth axiom from the first four. So here's another question. Out of these three people, whom would you say invented non-Euclidean geometry, if not Sakurai and Lambert? Gauss apparently was the first one to have these ideas, but never told anyone about them. Boyle was the first to have the ideas and really develop it, but he didn't really go out and make the public fight over it. Lobachevsky was the last person chronologically to come up with the ideas, but he came up with them independently himself, and he was the one that fought for them and got them accepted into mainstream mathematics. We now have like 5 possible candidates for the invention of non-Euclidean geometry. It's not an easy question. It's a very interesting, rich question about this. Okay, so what happened then? Even though non-Euclidean geometry was accepted as, okay, fine, it's just an alternate geometry, there was still the question of who cares? So what? If you picture lines, they behave in a Euclidean manner. So what good is developing all of this weird stuff? Oh, right, just saw in my notes. One thing I must say before we go on with this. Okay, I've got one, out of this whole series, I have one bit of homework for you. Here is the one bit of homework I have assigned for you. In the 60s, there was a musician, comedian, mathematician by the name of Tom Lehrer who made a song called Nicholas Ivanovich Lobachevsky. The premise of that song is that Lobachevsky stole non-Euclidean geometry from the Boyle. Now, we don't really think that anymore. That's not really the case, but this is an extremely popular song among mathematicians. I am sure that when I earlier introduced Nikolai Ivanovich Lobachevsky's name, his full name like that, most mathematicians couldn't hear that without singing to themselves, and Nikolai Ivanovich Lobachevsky is his name, hey! So here's my one piece of homework for you. Go on YouTube, find the Nikolai Ivanovich Lobachevsky song by Tom Lehrer, and listen to it. Probably even find it with the lyrics out there. It's great. And it's definitely part of the mathematical culture. Okay, now let's back up again. What was I getting into? I was asking, so what? You know, so you can reason this way. What does it mean? What is it about? Here's the question. What is it about? What does it mean? What is it talking about? You could do all of these proofs and all of these theorems, but you didn't have an answer to that. What are we going to get with this? Now, although it gained acceptance with Lobachevsky, it didn't really gain traction until mathematicians started coming out with different models or things to picture when you're talking about non-Euclidean geometry. So first we're going to, oh, I forgot to get this set up ahead of time. Hold on a second. The first thing we're going to look at is a model created by Beltrami, but was made sort of popular by a mathematician named Klein. Now it's usually called the Klein model, but it can also be called the Klein-Beltrami model. And let me just get this up. Okay, so let's say by the mathematical plane, we just mean this circle. and the points, we mean the points inside the circle, not the endpoints. Now let's take a look, and by point we mean a point, whoa, that doesn't work. By a point we mean a point inside the circle, whoops, point inside the circle. And by line, we mean line segment, or just a line connecting these 2 points, a chord of the circle that connects these 2 points. No, that's not what I mean. We just start talking about segment. There we go, line segment connecting points inside the circle. Now, first of all, let's take a look at Euclid's first axiom. Between any 2 points, you can connect it with a line segment. Yeah, that seems to hold. What about given a line segment, you can extend it? Now, as long as we're only allowing points to be inside the circle and not edge points, then sure, given any line segment, we can extend it. And similarly, you can show that the first 4 axioms of Euclidean geometry are true in this line segment. But let's take a look at the parallel postulate. Let's do this here. Let's say this here. Given 2 lines whose interior angles are less than 180 degrees, so like bam, bam, there we go, and bam, bam, bam. All right, let's just say I did that, bam, bam, whose interior angles are less than 180 degrees. If you extend them, they will eventually meet. Well, if we're only considering the area inside this circle, and we extend them, they will never meet inside the circle. So the 5th postulate, the parallel postulate, is false. So here is a way of envisioning a situation in which the first 4 axioms are true and the 5th one is false. Another one is one created by a fellow named Henri Poincaré, another big dang mathematician. Let me clear this out. Come on. All right, and what does Poincaré's model look like? Well, if we have a hyperbolic segment, his lines consist of circular arcs that meet the external circle at right angles. So if you have a circular arc that meets these outside of the circle at right angles, that's what's considered a line. And it is the case that given any 2 points, there is only one circular arc going through those points that meets the external circle at right angles. So given any 2 points, there is a unique line connecting them. And just like in the previous one, you can have 2 lines with a common transversal, and the interior angles of this common transversal add up to less than 180 degrees. But if you continue to extend those lines, they will never meet inside the circle. And in fact, since these are circular arcs, they might turn the other direction and start moving away from each other. So these are models in which the first 4 axioms are true and the 5th axiom is false. So therefore, these can be seen as models of hyperbolic geometry. When we're talking about hyperbolic geometry, we might be talking about these things. And after that, after you're able to actually picture them, hyperbolic geometry, non-Euclidean geometry got real traction. It really started going and becoming an area of enthusiasm and research. Okay, I've mentioned several times that there's a revolution, a Copernican revolution in mathematics, and basically this is it. Here is the big new idea. Until now, we thought about mathematics as being about things, about particular objects, triangles, numbers, and the question was, what's the nature of these things that mathematics is about? But now, we have this flexibility of interpreting what we mean by our words. When we use the word line, we might mean our normal Euclidean line that we're thinking of. We might mean a straight chord in a circle. We might mean a circular arc that hits that external circle at right angles. We're free to reinterpret what we mean by these words in different ways. And what we're interested in is if such a set of axioms, like Euclid's first 4 axioms, are true of a model, then what theorems are therefore also true of that model? We're not interested in what's true of triangles or lines, but we're interested in what theorems follow from what axioms. Because then these axioms can be interpreted in many different ways, and any different interpretation that makes the axioms true will also make this theorem true. So for example, Euclid went a long way before he finally used the parallel postulate. He put it off as long as possible. People take that as an indication that he kind of saw the questionability of it as well. He proved a lot of things before using it. For example, he was able to prove that every line segment had a unique midpoint. Now, since his proof that every line segment had a unique midpoint only used those first 4 axioms, that same proof will work in these 2 models of non-Euclidean geometry that we just looked at, in these 2 models that also satisfy those first 4 axioms. That same proof proves that if we take as our plane just a circle and our lines as just chords inside the circle, that same proof proves that any line segment has a unique midpoint. If we take the Poincaré model, the disk, and that we say that a line is a circular arc that hits the edge of the disk at right angles, that same proof from Euclid proves that every line segment in that model has a unique endpoint. So therefore, that one proof yields at least 3 truths. In fact, it might yield infinitely many truths. Any model you can come up with, you can sit down and come up with, that satisfies those first 4 axioms, it will also be true that any line segment in that model has a unique midpoint, because you can prove that using only the first 4 axioms, and we're assuming that you're coming up with a model in which those first 4 axioms are true. So we say that, if T is a theorem of a set of axioms A, then any interpretation that makes those set of axioms A true makes also that theorem T true. So this creates a huge power, a greater power in mathematics. Every proof could possibly be indicative of infinitely many truths. This leads to a great quote by Bertrand Russell about what mathematics is. I've got to share it with you now. In this vision of what mathematics is about, Bertrand Russell made the quote that pure mathematics consists entirely of the assertions of the effect that if such and such a proposition is true of anything, then such and such another proposition is true of that thing. It is essential not to discuss whether those first proposition is really true, and not to mention what the anything is of which it's supposed to be true. Thus, mathematics may be defined as the subject in which we never know what we're talking about, nor whether what we are saying is true. People who have been puzzled by the meaning of mathematics will, I hope, find comfort in this definition and will probably agree that it is accurate. You gotta love that. If you're ever looking for great quotes, Google up Bertrand Russell. He is a great generator of humorous quotes on all sorts of things. As far as quotes go, he's sort of like the Winston Churchill of the philosophical mathematical world. All right, so what do we get here? Now the thing is, this shift in view of what mathematicians are doing, and take it, some mathematicians now say, we don't need to answer the question of the nature of mathematical objects because mathematics isn't really about any objects anymore. Now, I consider this a dodge, and we'll get into this into later videos. But this definitely is an incredible shift in what mathematicians think mathematics is and what they're doing. And I'm saying that it is a Copernican revolution in mathematics. If you took a mathematician in the 1850s and put him in 1950 and showed him what mathematics was being done in 1950, they would probably say, this is not mathematics. There's a famous story of a young mathematician making his reputation by the name of David Hilbert. He gave a proof of something called the finite basis theorem. And an older established mathematician by the name of Gordon said, das ist keine Mathematik, das ist Theologie. He said, that's not mathematics, that's theology. And here we have, in the late 19th century, early 20th century, mathematicians, much less philosophers, throwing the accusation of mysticism against each other. Just like the Cartesians accused the Newtonians of being mystics for introducing this occult force of gravity. This theme is still going on. And like I said, and not even among philosophers, but even among mathematicians as well in recent history. Whew. So, if it's still confusing what I'm getting at by this transition, by this change, if it is still not quite clicking, the next video, we're going to keep chewing over it. We're going to keep looking at it. The next video, we're going to look at David Hilbert's Foundations of Geometry, in which he's basically summarizing up the current state of affairs of geometry in 1899 at least, not only including all of the gaps, filling all of the gaps that have been discovered in Euclid's elements over the last 2,000 years, but also looking at it from this new perspective. So we'll have an opportunity to look at what's going on from this new perspective a little more in concrete. And we're also going to look at the Hilbert-Frege debate, a series of letters going back and forth between Hilbert and another mathematician by the name of Gottlob Frege over what they were doing and whether or not it was legitimate, to help us sort of understand what this new perspective is a bit more. Okay, hope to see you there.